All right, let's work through it. So reviewing here, we've got this cubic that's in Z2x. And it is irreducible over Z2. Being a cubic, I can just check to see that it's got no zeros in Z2. And therefore, this ideal generated, this principal ideal generated by f of x is going to be a maximal ideal. That's a theorem. When f of x is irreducible over the field, the corresponding principal ideal generated by f of x is going to be a maximal ideal. Therefore, one thing you can say about the factor ring is that it is a field. That's one thing you can say about it. Reason being, again, is that since f of x is irreducible over Z2, we can say that the principal ideal generated by f of x is a maximal ideal. And therefore, it's a field. How many elements does it have in it? You can speak up if you like. Make sure I have my volume on. Yeah, okay, got it on. The hint's supposed to pretty much give it away. Nobody want to say? Looking at the hint, you can write the cosets of this factor ring, which is a field, in this form with these representatives, quadratic in general, where A, B, and C are in Z2. You got two choices for A, two choices for B, two choices for C. You've got 8 elements. In fact, this has 8 elements. I'm okay writing order notation. It's got 8 elements, 2 cubed. What could you then say about its group of units? The units being the things that have multiplicative inverses as a group under multiplication. How many such elements will there be? First of all, this is supposed to be easy, relatively speaking.
It would just be 8, right? The whole field.
Almost. You're thinking along the right lines, except you're forgetting one thing. Is 0 a unit?
No.
No, it's not. So the group of units never contains 0. So it's got to be 7 elements. One thing you can say about the group of units is that it's got 7 elements. And 7's prime. Hey, that means I can say something else. What's it got to be isomorphic to? Since 7 is prime. It's got to be cyclic, right? It's got to be isomorphic to Z7. And that would also mean another thing. That would mean every non-identity element in there has got to be a generator. What would the identity element be? Well, remember the operations multiplication. The identity element would be 1 plus A. That coset 1 plus A would be the identity. Everything else should be a generator. Should we? Let's go ahead and check that. See if we can check that. Let's try seeing if a 2 plus A is a generator. Start by squaring it. square root, you go ahead and you do 2 times 2 is 4, but we are modding by 2. Which would give 0, so I'm a little confused here. Oh, that's never mind. The coefficients are in Z2 to begin with. 2 plus A is 0. My mistake. Okay, let's try X plus A. What's X plus A squared? It would be X squared plus A. What's X plus A cubed? It would be X cubed plus A, but then you want to write it in this form. So do you do the usual thing? What is A? It's this. We know X cubed plus X plus 1 plus A equals A. That's equivalent to saying X cubed plus A equals negative X minus 1 plus A, but then mod by 2, that's the same as X plus 1 plus A. So X cubed can get replaced by X plus 1. This is the same as X plus 1 plus A. X plus A to the 4th. The X to the 4th plus A. And X to the 4th plus A, if you multiply both sides by X, is the same as X squared plus X plus A. X squared plus X plus A. X plus A to the 5th. So X to the 5th plus A. Multiply these by X, you get X cubed plus X squared plus A, but then that X cubed can get replaced by X plus 1. It's like this is X squared plus X plus 1 plus A, right? Replacing X cubed with X plus 1, just like I mentioned back here. Just 2 more powers and we should be back to the multiplicative identity, right? 1 plus A. X plus A to the 6th. I can just multiply everything here by X and get X cubed plus X squared plus X plus A. But then again, replace X cubed by X plus 1. Mod by 2, the X's are going to cancel to 0. This is X squared plus 1 plus A. Finally, this one should simplify to 1 plus A in the end. Multiply everything by X here, get X cubed plus X plus A. Replace X cubed with X plus 1. There we have it. X plus X would be 0. This simplifies to 1 plus A. Okay, so yeah, X plus A, for example, will be a generator of the group of units. And in fact, any other non-zero element is a generator as well, because that's what happens when you're talking about a prime order cyclic group, is every non-identity element is a generator. Did I clarify anything there? I know I went kind of fast with those calculations, but you've done some work with this kind of thing before. You just need to take the time to double check things. Here's a new question. Does f of x, the original polynomial here, have a root in this field? Is there any element of this field that is a root of this? Z2 itself, which it, by the way, is a field, right? Z2, 2 is prime, is a field with 2 elements. Z2 does not have any, well, no element of Z2 is a 0 of f of x. F of x does not have any zeros in Z2, but does it have any zeros in this field? That's kind of a strange thing to think about, actually. I mean, the elements of this field are things like this. I'm asking, are any of those things roots, zeros of this polynomial? The answer is yes. And at least one root is going to be this element here, x plus a. Let's see if we can figure out why. Is that x plus a, which again is x plus the principal ideal generated by x cubed plus x plus 1, is a root or a zero of the polynomial f of x equals x cubed plus x plus 1. So what does that mean? It means when I plug it into that polynomial, I should get 0. I've got to plug x plus a into the polynomial. So I got to compute x plus a quantity cubed plus x plus a plus 1, or really this 1 should be thought of as 1 plus a, because that is the unity in the field. This is the same as x cubed plus a. And then when you add cosets, you add their representatives, you get x cubed plus x plus 1 plus a. But hey, a is generated by x cubed plus x plus 1. Giant sucking sound. This is the same as the ideal itself. It's the 0. That does it. That proves x plus a is a 0 of this polynomial when interpreted correctly in this field. Interesting. And true. And that will always happen, actually. If you got a polynomial that's irreducible over, say, zp, where p is a prime, and if it's cubic in particular, so we know it's irreducible if it's got no zeros. That would be the case also if it were quadratic. Then in the factor ring, which will be a field, this element, x plus the ideal generated by the irreducible polynomial, will be a 0 of that polynomial. That will always happen. And the calculation that we just did here kind of makes it clear why. You end up getting the polynomial itself in front of the plus a. It is the coset representative, and it has to get sucked in. Here's something else to think about. This thing right here, this field, can be thought of as what's called a field extension of Z2. What does that mean? Well, it's just another way of saying, i.e., Z2 can be thought of as a subfield of this factor ring. This thing being a field extension of Z2 is equivalent. It means the same thing as saying Z2 is a subfield of this. And what do I mean can be thought of? Well, thought of after making a certain natural identification. Essentially, think of 0 in Z2 as being identified with 0 plus a. Well, let me redraw that. 0 in Z2. Think of it as being identified with 0 plus a in this factor ring, which is a field. And 1 in Z2 can be identified with 1 plus a. Where the 0 and the 1 here and here really are constant polynomials. Here they're numbers, just in Z2, think of those elements as numbers. Here we're really thinking of the 0, 1, and the 1, these coset representatives, as being from Z2x, so they're really polynomials, constant polynomials, but it's such a natural association to make that we do go ahead and do it. We do go ahead and think this way. And so in creating this field extension of Z2, where Z2, well, where f of x had no zeros in Z2, we have created a field extension of Z2 in which f of x does have a zero. That's going to be a real common theme for us here, these last 2 weeks of class. Thinking about polynomials that don't have any zeros in some field and creating what's called a field extension in which the polynomial does have a zero. As a non-modular example, this symbol right here, we've seen this before, although I think the book initially used a notation with square brackets around the square root of 2. This is called the field of rationals adjoin root 2. And how do I spell adjoin? I don't know if there's a D in there or not. I think there is. A-D-G-O-N. Yeah, G-O-I. J-O-I-N. Adjoin square root of 2. By definition, it is the quote unquote smallest field extension of Q containing square root of 2. What do its elements look like? Its elements are linear combinations of the number 1 and the number square root of 2. A times 1 plus B times root 2, where the coefficients, the scalars, you might say, of a linear combination are rational numbers. This is a field extension of the rational numbers that contains root 2. Notice it contains a lot more than just root 2 beyond the regular rational numbers. It contains 2 root 2, it contains 3 root 2, it contains 1/2 root 2, negative 17 13ths root 2. In fact, any linear combination like this of the number 1 and the number root 2. So it's not just the rationals and one more element, okay? There's infinitely more elements that are being combined with the rationals to form this set. And this set is a field. Maybe that's not obvious that it's a field. Becomes a little bit more believable if we try to figure out the multiplicative inverse of an arbitrary element. What's 1 over a plus b root 2 equal to? And can I put it in this form? I better be able to if this is going to be a field. It's got to be closed under multiplicative inverses. The way to figure out what this equals is to do a little trick to multiply this by the disguised form of 1, and the disguised form of 1 will be a minus b root 2 over a minus b root 2. Sometimes called the conjugate of a plus b root 2. And why do I do that? It's because when you do that, when you FOIL out the bottom, the root 2's go away. First times first is a squared. Outside times outside and inside times inside cancel completely. And last times last is negative b squared times 2, or minus 2b squared. And the top is just a minus b root 2. And this can be rewritten as a over a squared minus 2b squared minus b over a squared minus 2b squared times root 2. And because of the fact that root 2 is not rational, you're not dividing by 0 here. There's no way when a and b are rational that a squared minus 2b squared is going to be 0. So, well, unless they're both 0. But I'm implicitly assuming a and b are not both 0. Either a is 0 or a is not 0 or b is not 0 here. So what I've now ended up with is some rational numbers plus, if you want to think of this as adding a negative, some rational number times square root of 2. It is in this form. So that is not a proof, a complete proof that this is a field, but it helps you believe it. That this is going to be a field. Very important kind of field for us. Okay. Got to make a big deal out of this kind of thing. And whereas x squared minus 2 in qx is irreducible over q, it is reducible over this new field q adjoin root 2. X squared minus 2 can be factored as x minus square root of 2 times x plus square root of 2. Over that field. So we really have done the same kind of thing we did with the other example. We started with a field. In the other example, it was Z2 and a polynomial. It was x cubed plus x plus 1 in the other example. Here in this example, it's x squared minus 2. That is irreducible over the base field, Z2 in the first example, Q in this example. But I can create a bigger field, a field extension, in which these things do have roots. And when you go back to the historical origin of algebra, one big thing way back when, 1500s especially, people were trying to figure out how to solve general equations, and they'd solved quadratics for a while. They knew about completing the square and technically the quadratic formula for a long time, but they didn't know how to solve cubics or fourth degrees. And so this is the kind of thing that they were thinking about, and this is the historical origin of field theory, is trying to solve algebraic equations. And the main theme being keep making a bigger number field where you've got solutions. As another quick example, x squared plus 1. Oh, let's go ahead and imagine just being in Rx. is irreducible over R, the real numbers, but reducible over C, the complex numbers. X squared plus 1 can be factored as x plus I times x minus I, or I squared is -1. And we don't have to worry at all about philosophical questions. Does I really exist? Does this imaginary unit? I mean, it's called imaginary unit for a reason, that people thought of it as just a questionable kind of thing way back when. That's the origin of calling it the imaginary unit. People said, this is just an imaginary thing that we're using to do things. And so the name stuck, but it's just as real numbers are, okay? There's no philosophical question about whether it exists or not. We define it to exist. We create these algebraic systems that have all these properties by definition. Whether they're useful or not is another question. Is it useful to be able to factor x squared plus 1 like this? It turns out it is. Turns out there are many applications of imaginary numbers. Lots of surprising applications, in fact, in physics, for example, quantum mechanics. So there's no philosophical issue about existence. The only question is it useful? And it turns out that it is. All right, to end class today, we're going to focus on something else, chapter 19. This is really a preview of after chapter 19. What is chapter 19 about? Chapter 19 is a short chapter about vector spaces. In other words, linear algebra. But it's done a bit more generally than you'll find in your linear algebra book, is the main thing to watch for. When I talked about this field here, Q adjoin root 2, and I described it this way, I purposely used some linear algebra words. I described this as the set of all linear combinations, right? That's a word from linear algebra, linear combinations of 1 and root 2, where these coefficients, I also call them scalars on purpose. These scalars are rational numbers. This is a vector space. It's a vector space whose elements are from this field, and whose scalars, when we think of the elements this way, are rational numbers. Q adjoin root 2 as a set. Again, it's the set of all numbers that can be written in this way. Is a vector space over Q itself. What does that mean? Again, it means its elements can be thought of as vectors in the sense that you can add them. The addition satisfies the associative property. It's commutative addition, actually, just like the fact that this is a ring means the addition is commutative. It's got a zero vector. The number 0 is the zero vector. If you take A and B to be 0, it's got additive inverses. The additive inverse of root 2, for example, is negative root 2. We already know this is a group under addition. Those same properties under addition hold for this as a vector space. But being a vector space, we ignore the multiplication of arbitrary elements in this field, but instead focus on the fact that we can multiply, we can write things in this field in this form as a linear combination where these coefficients, the a and the b, are rational numbers. That's why it's a vector space over Q, is because those scalars are rational numbers. In fact, using notation from your linear algebra book, we could call this span 1√2. Remember span, your old friend span? I'm smiling. Your old friend span from linear algebra, right? The thing that always made you feel kind of scared. What is span? Span is the set of all linear combinations of whatever's in here. Actually, our textbook doesn't use the span notation. Instead, it uses the pointy bracket notation again. But it means the same thing. It's the set of all linear combinations of these two elements, where the scalars, coefficients, are rational. Not real numbers, not complex numbers, but rational numbers. We could ask, is this set of two vectors a basis for this vector space? And the basis? What do you need to be a basis? You need to span the space. Hey, that's already happening. And you also have to be linearly independent. Oh boy, linearly independent. We already know it spans. By definition. Since by definition, I could write everything in this as this linear combination. That's what this Q adjoin √2 is. Is it a linearly independent set? If a linear combination of 1 and √2 equals 0, does that imply the coefficients are 0? A times 1 plus b √2 equaling 0, does that imply a and b must be both 0? That's what linear independence would mean. If a and b must both be 0. And yeah, it's because √2 is irrational. There's no way you're going to get 0 unless both a and b are 0. A and b are rational numbers. If you set this equal to 0, that would be equivalent to saying a equals negative b √2, which would be equivalent to saying a over negative b equals √2, assuming b is non-zero. But that's not possible because √2 is irrational. It can't be a rational number. A and b are rational numbers. This is impossible. Therefore, a and b are both 0. Therefore, this is a linearly independent set. Therefore, this two-element set is a basis for Q adjoin √2 over Q. And therefore, the dimension of this vector space, Q adjoin root 2 over Q, maybe we want to put like a subscript of a Q here. This dimension is 2 because it's got a 2-element basis. That's what dimension of a vector space is. It's the number of elements in any basis. It's a theorem. In fact, it's the only theorem listed in chapter 19 that if a vector space has one finite basis, then any other basis of that vector space has got to have the same number of elements. That allows us to uniquely define the dimension of the vector space. This theorem right here is the only theorem in chapter 19. If U1 through UM and W1 through WN are both bases, plural of basis, of a vector space V over a field F, then M must equal N. If a vector space has a finite basis, then any other basis must be finite and have the same number of elements, in fact. And that allows us to define the dimension. A vector space that has a basis consisting of n elements is said to have dimension n. For completeness, we say the trivial vector space is said to be spanned by the empty set and have dimension 0. The 0 vector being a part of a set makes that set always linearly dependent. So you can never have a basis with the 0 vector in it. But by convention, we say this vector space is trivial and has dimension 0. There are infinite dimensional vector spaces. That was mentioned here, but here's an infinite dimensional vector space. There's lots of examples I could pick here. Let's just go ahead and pick Rx over R. That would be one example of an infinite dimensional vector space. It doesn't have a finite basis. This is the set of all polynomials with coefficients in R, like usual. If you think of those polynomials as being vectors that can be added, and then, we already know it's a group, an abelian group under addition. We can definitely do that. We can also multiply them by scalars, real scalars, and get another such vector, C times an arbitrary polynomial. You multiply each coefficient by C. Why is it infinite dimensional? Well, because the degree can be arbitrarily high. Does it have an infinite basis? Yeah. These polynomials, this set of polynomials forms an infinite basis. This set is linearly independent. If you got a linear combination of a finite number of these that equals the 0 polynomial, the coefficients must all be 0. And it would be would span this infinite dimensional vector space. Give me any polynomial. It's got a highest degree somewhere. Say it looks like this. You are, by definition, you can write it as a linear combination of those powers of x. But because the powers can be arbitrarily high, this is an infinite dimensional vector space. The key difference between this definition right here and the definition of a vector space in your linear algebra textbook really is with regard to where the scalars come from. The scalars come from an arbitrary field. If you look in your linear algebra textbook, the scalars are assumed to be real numbers. Well, I think there might be one part of the book where they say consider complex scalars. But for the most part, in your linear algebra book, the scalars are taken to be real numbers. Here, yes, the real numbers do form a field, so that is one example of a vector space that we can make over a field. But we're allowing any field here. Could be Z2, could be that simple of a field. That's the main difference between this definition and the definition in your linear algebra book. Otherwise, it's pretty much the same, although we're emphasizing the properties of just addition by saying V is an abelian group under addition. Just like a ring is. Okay, any ring is also an abelian group under addition. So any vector space is an abelian group under addition. Whereas in rings, you have a multiplication in the ring itself. With vector spaces, you have a multiplication, but it's not in the ring itself. In fact, we're ignoring the ring properties. Even if V happens to be a ring, we're ignoring those properties. We've got some outside field with scalars, and we're multiplying A times V, where A is a scalar from F and V is a vector in V. So the closure here, the binary operation going on, is a different kind of binary operation. The scalar multiplication binary operation is of a different type. As a binary operation, it means it takes two things and gives you a new thing. But in this case, you're taking an arbitrary element from this Cartesian product and mapping it to something in the vector space. With a ring, this Cartesian product would be V cross V. With a vector space, this Cartesian product is F cross V, where F is a field and V is the vector space. Give me an ordered pair, a scalar and a vector. I want to map it to some vector. I call that vector AV. Why do we call these things scalars? Well, it goes back to physics in that, you know, if you're thinking of a vector as an arrow, maybe drawing a little half arrow head above it to emphasize it's a vector, then 2 times the vector is twice as long in the same direction. Pretend that's the same direction. That's the origin of the word scalar, is scalars rescale vectors. But as in your linear algebra book, when we're talking vectors, the theory of vector spaces, we're not necessarily imagining vectors as being arrows. The dimension of the vector space, by the way, does depend on what the field is. C, the complex numbers, all numbers of this form. That is the same, by the way, as R adjoin I. This is a 2-dimensional vector space over R, the real numbers, with basis 1i. However, it's a one-dimensional vector space over itself. C is a one-dimensional vector space over itself. In fact, any field is a one-dimensional vector space over itself. What would a basis be in this case? Well, take any non-zero number, like 1, and that'll be a basis. Why? If I'm allowing my scalars to be complex numbers to begin with, I can form any complex number as that same complex number times 1. If I'm allowing my scalars themselves to be complex numbers, then I only need a basis with one element, and in fact, any non-zero number would do. But certainly picking a 1 is the simplest thing to pick. Whereas if I'm here, if I'm only allowing my scalars to be real numbers, to write an arbitrary complex number a plus bi as a linear combination when your scalars are real, you need 2 vectors. And this is the simplest one, 2 numbers, 1 and I. It's not the only answer, it's just the simplest. You remember that in linear algebra? And in general, there's always infinitely many different bases you can pick, but the standard basis is the simplest one, is the one you usually pick. But we can write down this generalization. Any field F is a one-dimensional vector space over itself. The multiplication in the field is the same as the scalar multiplication, if that's not clear. Fields, of course, have an addition and a multiplication. They are rings. If I think of that multiplication as being a scalar multiplication, which I can do if I want, then it becomes a vector space over itself. Final comment for today, and we'll end class a little early here, is any field, let me call it E, is a vector space over a subfield F. Said another way, given any field F, any field extension E is a vector space over F. Given any field F, any field extension E over F is a field, or is a vector space over F. E is the bigger field. You can maybe picture it like this. Here's F. E is the bigger one. E is a field extension of F. Notice I did not say what the dimension is, because the dimension depends on the example. This example is emphasized in chapter 19. It's example 5. They say, although it appears rather trivial, it is of utmost importance. Let E be a field and left be F be a subfield of E. Okay, I guess they write it in terms of subfields here. Then E is a vector space over F. The vector addition and scalar multiplication are the operations of E. The multiplication of an element of F by an arbitrary element of E is what you're thinking of as being the scalar multiplication. So it's easy to get confused here, okay? The examples should help. Make sure you study those. And in the practice problems, there is at least one problem, maybe a couple problems where you should go back and do row operations like you did in linear algebra to help answer questions. And sometimes those row operations in a matrix can be done with mod P. All right, that's it for today. Have a good day.
Wednesday.